Hello, in this video we're going to compute another limit of a sequence. In the sequence given here, we now have, again, a rational function, only the numerator has a higher degree than the denominator, which should be a tip-off right from the start that this sequence should diverge. Right? When the degree of the numerator is bigger than the degree of the denominator, then the numerator should be growing much faster, right? At least in absolute value, and then the denominator should be, right? So we should expect that this is going to diverge. But let's give a better argument for it. So we'll look at this ratio, n squared minus 1 over n, and I can multiply, well, there's sort of two reasonable choices. Hey, maybe we can multiply top and bottom by 1 over n squared, which is the highest power of n you see anywhere. Or maybe we should multiply by 1 over n top and bottom. And in this case, either one will give us an answer, but we're going to use 1 over n this time. It should make our life probably a little bit easier. So when I multiply on the top, of course, I'm going to have to distribute. N squared times 1 over n will just be n, minus 1 over n. And then on the bottom, n times 1 over n is 1. And this is why I chose to multiply top and bottom by 1 over n, is it essentially eliminates the denominator. So I just have n minus 1 over n. Now, we were told we could assume without proof if you have something of the form 1 over n to the k, where k is positive, and we do here, 1 over n, right? That works, that's k equals 1. This part will converge to 0. Hey, that's a good start. Except there's still this n over here, and n is just blowing up to infinity. So you have one component going to infinity, the other part is going to 0, and of course then as n goes to infinity, this difference will also go to infinity. And so we conclude that this sequence does not actually have a limit, it diverges to infinity.